All right, good afternoon, everybody. Welcome back to another live stream. This one is a pretty exciting one, and there's a lot to cover today, so we are going to dive right into things. So, just a little context on what we are going to be doing today. So, let me go ahead and show my demo station over here. So, as you know, we are continuing along with our computer vision parking lot project here. And so, off to my right over here, I have this demo station with this web camera that is facing straight down. This is a live view right now that you can tell because you can see my hand waving over here. And basically, what we're doing here is we're going to be taking at the end of this project, we're going to be using this webcam to detect when a car enters the parking lot and parks in a parking space. So that way we know how many of these spots are actually open and how many are actually filled. So in the last stream that we covered last week, you might recall that we did some basic image processing with OpenCV. And so in this next live stream, we are going to be taking it to the next level by, because what I basically want to do at the end of this project is when we start up our Python script that's going to represent this detection whole thing is I want to have two different screens going on. I want to have one screen, the real-time feed of showing the cars coming into the parking lot. And obviously, this is not a real parking lot. This is just some tape on a piece of paper that I made. But so starting up like that and showing the cars as it comes in. But I also want to have a second window that actually shows a diagram image, like representation of what the parking lot looks like. And so what we're going to be doing today is actually using OpenCV to actually detect the parking lines, in the parking space, the empty parking spaces automatedly. So I think I mentioned last week, the reason that, this kind of project really thrills me is that prior to becoming a machine learning engineer, I thought I wanted to be a graphic designer, and I still am really interested in graphic design. So this is really marrying the best of both worlds, and my camera is not on center. Why is it not? Hold on there. Sorry, folks. Is that better? I think so. What is this red thing? Oh, that's my straw. Sorry. All right, yeah, so graphic design, I really do like it. So what this is actually going to be doing is basically, so I could statically create a diagram that represents this over here, but that is not really replicable. Now, to be completely honest, the tactics that we're going to be doing today aren't super replicable for any, generalized parking lot too. The goal here is to get you some familiarity with a number of different functions of the OpenCV library so that, because I think if I really, really, really tried, I could probably make something that is more general that is, I always think this is probably a pretty dumb analogy, but throwing out some, like a little cube almost that's like a metal cube, and then you just toss it out and then it forms into this robot like thing. I basically want to kind of do that with our camera over here. Is I want to just fire up this camera and it here, let me show the demo station again. Fire up the camera, it looks at the parking lot and it draws the lines for us. So I'm not going into one of my graphic design pieces of software like Affinity Designer or Adobe Illustrator and pre-creating that. That seems a little bit cheating, and it's not really useful because the goal would be, let's say I'm a parking garage owner. I don't want, and obviously parking garages have multiple levels to them. And, most parking garages have one or two cameras on each level, maybe even more than that. I don't want to have to create a diagram for each single level by hand. I just want to fire up this camera and I want it to detect the lines for me and detect the empty spots. That way, so somebody's not manually having to do that for me. So that's what we're going to be covering today. And again, this is really going to be more toward the narrow use case of what we're going to be doing with our model here. But will hopefully give you an idea of what maybe you could do for your own use case if you wanted to, or if I ever wanted to expand on this project. So again, we really are just diving into things here because there's a lot to cover. And I really want to hit the ground running here. So let me go ahead and share my regular screen. Okay, get that out of the way. All right, let's go ahead and fire up a Jupyter notebook. So, oops, repos, CD, CV parking lot, ls. All right, so Jupyter notebook. Okay. All right, let's go ahead and make this full screen. Notebooks, and let's create a brand new notebook here. I'm going to call this parking diagram live stream. I guess it doesn't really matter because I'm going to delete this notebook right after the live stream. I mean, to be honest, you know, I've mentioned this before. Even though we do live code these three things in the live stream, I do pre-prepare these things beforehand because I've tried coming into these. Well, some of you have seen this before. I've tried coming into these things legit live, and those streams are always a train wreck. So I've decided no more live streams. Instead, I do a little bit of pre-preparing, but I am going to live code this thing, and I'm just going to delete this notebook. But if you go out to my GitHub right now, github.com/dkhundley, or if you just go to dkhundley.com, that goes to a link tree that goes to, you know, you can find my GitHub there. Then you can actually see this full Jupyter notebook with a bunch of Markdown already created inside of it. And we're basically going to be replicating that exact same notebook here. Okay, so the first thing that we need to do is we need to open, or we need to import some of our libraries. And these are going to be the same libraries that we used in our last stream. So as a reminder, we are going to be using OpenCV, which is represented as CV2 here. So this is the one that's going to be doing the heavy lifting for us. This is definitely the one we're going to be using the most often. I don't remember if we used this last time, but for those of you who are familiar with the data science community, you will definitely know what this library is. So this is NumPy, and what this is it's a way to do complex computational mathematical calculations very quickly. It's written on top of the C language, and you know, so whenever, you know, when these images are loaded up, they are loaded up as arrays of numbers, and we are actually going to use NumPy this time a little more extensively, not super extensively, but we are going to use NumPy to do some transformations in some specific ways. And then finally, you know, we are going to import matplotlib.pyplot as PLT. And the only thing, you know, matplotlib again, I did this exact same thing last time. I forgot to put the lib. All right, matplotlib inline, and you know, this is the general purpose library that we use for like data visualizations in general. However, for the specific case of our notebook, we are really just going to use it just to visualize our images as we go along. Okay. So that is importing our stuff here. Not sure. Okay, there we go. All right. So the first thing we're going to do is we are going to import the raw image. So this is the same raw image that we worked from last time. Hold on, folks. I got to sneeze here. I think I got to sneeze. Okay, maybe not, or maybe I do. Don't you hate it when that happens? Like when you think you got to sneeze and then you don't. Okay. I still feel like I got to, but we're going to power through it. All right, so let's go ahead and load up the raw image. So this is the same function that we did last time. I still feel it coming on. Okay, it's gone. All right, hopefully it does not come back. So the way that we read in these images is with the mread. And so I have this image stored in my data raw directory, and this is called the parking lot image. Now, if you recall correctly, OpenCV, I don't know why it necessarily does this, but it reads these images in the color formats of blue, green, red, BGR. If you are familiar with computers, you will know that most computers like the color channels to be in red, green, blue. So if we just let's go ahead and look at this image right now. So raw plt.imshow raw image. This is obviously looks weird because the color channels are backwards here. So what we need to do is first change this to the correct color channel. So raw image equals cv2 convert color, cvt color. I'm going to pass in the raw image, and then cv2 dot color bgr to RGB. By the way, I am monitoring both YouTube and LinkedIn for questions, so if you have any questions along the way, feel free to drop them in the chat, and I'll answer them along as I see them come in. Okay, so that's how we do that, and then let's go ahead and show that raw image again. I'm just going to rerun this cell because I'm lazy. All right, so you can see that that looks fine. Now, we do need a grayscale version of this image, so let's go ahead and show that. So gray image equal, or let's go ahead and convert that. So same conversion again here, just a tiny bit different this time. So gray image equals CVT color. raw image cv2.color RGB to gray. Okay, and then if we want to show that, it's PLT imshow gray image. Now, if you recall as well from our last stream, whenever we show grayscale images with this plt.imshow function, by default it shows it in this Viridis color format. So I'll just go ahead and show that. That in the Viridis color format is this really weird, like teal to greenish to yellowish kind of format. And so the easy way to correct that is by setting the CMAP value, aka the color map value, to be gray. And now we get a grayscale version of our image. I don't know why that looks so weird though. Does that look off to you all? That looks off to me. What is going on here? All right, let me rerun some solves here. Okay, I don't know what happened there. Maybe I, okay. So here's a side tangent. Let me get on my soapbox for a second. I love Jupyter notebooks. I really do. However, if you are going to productionalize something, please don't use a Jupyter notebook or give me a Jupyter notebook. And the reason for that is just like you saw here. I ran the cells out of order, and this is actually a pretty common thing that I've seen, is that people, by accident, people don't do this intentionally, they run the cells out of order. And so that's why, Jupyter notebooks are fantastic for discovery or for teaching people things like this, or, teaching things in Markdown. But whenever if you hand this over to a colleague, for whatever reason, you got to be really careful about the order that you run the cells in, because clearly I did something goofy there and that messed things up. So, all right, stepping off my soapbox again. All right, so now we have the grayscale image. So the first thing that we want to do, so by the way, again, this is where I think this part of the project comes in, where we're going to have a lot of creativity here. The way I'm going to be doing things is not necessarily the right way. In fact, I would say there is not a right way to do things. The goal with this effort here is to show you one way to do things, or it's actually showing you a multitude of tools to get you toward the end product of how to do things here. And so, I'm not going to say my way is necessarily the right way, because my way is only going to work for this piece of paper over here. If I were to go to take my camera to Walmart and take a picture of the parking lines at Walmart or Sam's Club or wherever, this probably won't work here. And it's because, again, this is not generalized enough for multiple things. But the nice thing about what we're going to do here is I'm going to teach you some tools here, and by understanding these tools, we can build an intuition around, okay, now that I understand these tools better, can I start to put the pieces of the puzzle together better? And so that's actually what happened with me. I took this another plug. I've given this plug before. Jose Portilla, or Portilla, as it is spelled phonetically, over on Udemy, has a course called Computer Vision, OpenCV Computer Vision, something like that. Basically, everything I learned here is, or I would say 90% of the stuff that I'm going to be showing in this demo today is from. I learned from that project. However, I basically took the tools that he taught disparately in different sections and applied them in different ways and combined them all together. And then I did learn a couple things that he actually did not teach. But excellent course, highly recommend. I'm talking with my hands a lot today. So one of the things that we did in our previous live stream with the image processing is we did a color equalization. So if you recall what that was flattening. And in fact, I actually do have the notebook here, so I guess I could go ahead and show that. Okay, so what that did here, so this is the histogram of the original raw image, and if you recall, this is basically the color equalization is going to flatten out the colors here, so where it creates a higher contrast, and that produces an image like this. So as you can see here, this produces a very vivid yellow color here. And so that is actually ideal here, because that is going to be easier to grab this yellow color that represents the parking lines. So the first thing that we're going to be doing here actually with our project is we are going to be grabbing the parking lines before we grab the actual parking spaces. Okay, so let me close out that notebook. So the first thing that we're going to do is the exact same equalization that we did in our previous project. So the first thing that we need to do in order to do the equalization is we need to convert our image from RGB to HSV, just because that's how you do it. So I'm going to do the HSV image equals cv2.cvt color, raw image cv2 color. So the nice thing about this is, you know, the conversions are pretty easy. It's pretty much always this, you know, CVT color. You pop in whatever image you want to convert, and then you do the cv2.color underscore, and then you do the source to destination. So in our case, it's RGB to HSV. I got to type the letter V there. Okay, so the next thing that we have to do is we actually have to apply the equalize histogram function in order to actually like equalize the values of the histogram. So so the way that we do that is HSV image. And so the syntax here is a little bit goofy, so that's why I do have this pulled up on my other screen, because I definitely do not have this part memorized. So cv2.equalize hist. Same thing here. All right, colon 2. Okay. Now okay, so that is our equalized image. So I do need to convert that back to RGB again. So the way that we do that is equalized image equals cv2.convert color. A lot of color conversion going on here. I don't think we're gonna do too much color conversion in the remainder of this project, but we might. I guess you do have to do a lot of color conversion just depending on your use case. And I always forget that too. cv2.color. Okay. HSV to RGB. Okay. And let's go ahead and display that. So plt.imshow equalized image. Okay. So all good to go. So now we have, this is the exact same thing that we produced at the end of our live stream last time. Okay. So now what we want to do is we want to extract that yellow color, because that yellow color really pops from the rest of the background. So, you know, it is very clear where the yellow lines are at as compared to, you know, we have a, we do have some lighter color over here with white. We have some darker color over here with black, but we can extract the yellow color out here quite easily. So first thing that we need to do is we need to set some boundaries of like where we expect the yellow range to be. So remember, we are working with RGB color values. So I already did some pre-Googling beforehand to figure out like what are some ideal color values to figure out like an upper boundary and a lower boundary of like what represents the general spectrum that defines yellow. So let me go ahead and define those. So I'm going to call this lower yellow. So this is going to represent our lower yellow boundary. And so here's where we start to introduce NumPy. So we're going to use this function of NumPy called NumPy array, and that's going to basically instantiate an array of NumPy values. Again, this is RGB, so 22, 93, 0. So this is going to be our lower boundary. So D type equals uint 8. So basically what this is doing is creating an array with these three values of type integer of an 8-bit value. Okay, and so and then we need to do the same thing for our upper yellow boundary. So upper yellow equals np.array. And again, I do have these static values. I'm just looking at my other screen below, just defining what I want to be the upper value to be. So I actually didn't look at this super closely, but when you see 255, 255 like that, it looks like it's just trying to get a lower yellow value and then basically anything above that. Or maybe I'm misinterpreting that. I honestly just found these these values Googling. I probably found them on Stack Overflow more specifically. But yeah, thank goodness for Stack Overflow. You know, you all can relate to that, I'm sure. Okay, so that's setting the upper and lower bounds. So the way we actually, so this is one of the things that actually I did not learn from Jose's course. Again, Jose's course was great, so highly recommend it. We're going to use this function that is basically, we pass in our image and we pass in the upper and lower bounds, and we get back the image that we're looking for. But I forgot that we actually have to use the HSV image in order to do this, because I'm looking at my code down here. Again, I'm not really sure why sometimes we have to use one versus the other. There probably is a mathematical reason of why. So we're actually going to use the HSV image whenever we're actually looking for these values. And when we actually get the values back, it's actually going to give us black and white, a grayscale image. So let's go ahead and do that. So the way we're going to do that was, I'm going to call this parking lines. Parking lines equals cv2 dot, and so this function is called inRange, and so we pass in our HSV image, and so then we pass in the lower bound, lower B equals lower yellow, and then upper B equals upper yellow. Okay, now let's go ahead and take a look at this plt.imshow. Parking lines. So this is a grayscale image. So we need to set the CMAP to equal gray. All right, so there we go. Now this is basically our parking line. So that is, that is part one of our project. So, this is probably the easier part of the project. So, the next part is the fun parts. But before we move on to the next part, which would be detecting the actual spaces itself, recall that at the end of the day, I want to create a representative diagram that kind of looks similar to, but not exactly like the actual real picture, meaning that I want to set the color values of this thing to look like the real deal. So I don't want it to be white lines on a black background. I want it to be yellow lines on a gray background. So again, so in the graphic design world, it is very common for people to go online to these different color-based websites to understand different different colors specifically. So I think you all can relate more specifically if you've all ever painted your house. Like if you've ever gone to Lowe's or Home Depot and you've looked at all the color swatches and you grab one, like you grab the blues and it's got like 5 different shades, and one's like cerulean blue, ocean blue, and all these different kinds of blue, and they're all super close, but they're all a little bit different. I believe, and I might be wrong about this, but I believe there's 2 numbers in the corner. One is representing the hexadecimal value, and then the other one would be the RGB value. So the RGB would be represented by the 3 colors. And so the graphic designers often do this online. So I actually went online. Let me see if I can grab this link here, copy link, and to look for what was representative of a good yellow and a good gray. So I'm just going to show the yellow one real quick. We're not going to spend too much time looking at this from this website. Uh-oh, didn't mean to do that. Oh, I just copied the bare link. That's not what I wanted to do. Hold on. All right. Okay, so this is this website called colorcodes.io, and I just Googled something like, I want RGB yellow parking lines, and it came up with this one. So this is the color that I want to talk about, or take. So this is what I was referring to, and I'm pretty sure that this is the case for paint swatches that you pick up, is that you get all these different color values, and I forgot about CMYK, but we're not going to talk about CMYK. Don't necessarily worry about that for this presentation. So yeah, we do have the different values. For my graphic design work, or even if you all watched my data visualization presentation on with Halloween candy a couple weeks back, we use the hexadecimal values. I actually do prefer the hexadecimal values. It's just that CV2 is more privy toward the RGB values, which is fine. So I went ahead and copied these static values, and I did the same thing for the gray. So I found this is called road sign yellow, and the other one I believe is called like asphalt gray or something like that. Yeah. Ooh. I am doing a lot of talking. I'm a little bit winded. I don't know if you can tell, y'all. So, okay, sorry. I was just taking a minute to breathe there. Okay, any questions? Oh, I take a sip. Okay, so what I'm going to do here is I still need these lines here as the parking lines in this format. So what I'm going to do here is, remember, this is still in a grayscale format, so I need, whenever we actually colorize this, I need it to be in an RGB format. So I'm going to call this colorized parking lines equals CV2.CVT color. We're going to pass in the parking lines, so the same thing that we just defined above. CV2 dot. Okay, so maybe we are going to be doing a whole lot more color conversions. So yeah, this is, I guess, more common than I thought it would be. All right, so we colorized our things here. Now, I'm going to create a little markdown cell here really quick. Markdown, so you all know what I'm doing here. All right, I'm just going to copy in these values. Oh, wait, I can't do that because this is HTML, not not the other thing. Okay, so these are the values that I'm going to just for reference. So I want road sign yellow. I want asphalt gray. Here, let me move my face up so you all can still see. All right, so I want these two values. And so basically we are going to be, recall that this is these images, or I'll even just show this really quick. So colorized. So, I mean, this isn't showing this very well. Well, I guess it kind of is, but all of these pixels that represent this image here are basically just arrays of color values. So this is in the RGB color format right now. So, you know, the RGB will have 3 color channels, which is why we see 3 array values here. So these are all, we're mostly seeing zeros here because the zeros represent the black. Now, if we did show the lines here, it would show like ones. So basically we're going to, and because these are all represented by numbers, recall that when I talked toward the beginning that we imported the NumPy library, we're going to be using NumPy here to actually change the color values of specific things to a different color value. So basically we're going to say, okay, anywhere that's 0.0, or I'm sorry, not 0.0, 000, aka the representative of the black, we want to change it to 128, 26, 120, which represents asphalt gray. And so and then 255, 255, 255, which represents the white color, we are going to change to 253, 218, 220, or 253, 218, 22, which represents road sign yellow. So, make sense? I hope it does. Okay, so the way that we do that here is, so let's go ahead and do the yellow lines first. So this is our parking lines. So we are going to use this function within the array here called numpy.where. So where colorized parking lines equals 255, 255, 255 dot all axis equals 2, because we're trying to grab the value where it is appropriate. Just making sure that my so basically it's saying where all these values equals 255, 255, 255, again where all the white parking lines are at, we now want it to be this new value. So what is that? 253, 253, 218, and 22. Okay. And we're going to basically do the same thing here. So I'm just going to copy and paste again, but this time, anytime where we see 000, which is the black background, we're going to change the black background to be 128, 126, 120. Okay. So notice that I did not save that back to a variable because we're not changing the overall variable. We're just changing the values associated to the array within that same variable. So we did not do any new assignment of any variables here. So let's go ahead and view this. So plt.imshow colorized parking lines, and you can see there we go. That is our same parking lot that we see here in a binary. And when I say binary, I mean there's only 2 colors represented here. There is just gray or just yellow. So step 1 done. And honestly, that was the easier part, because the reason it was easier is because the yellow is very defined. And you know, after we applied the color contrasting here, it was very easy to do this thresholding with the upper and lower values of the yellow to say, okay, just grab that color and then you know, set the thresholds appropriately. Now, here's where we get a little bit tricky with trying to detect these spaces. There may be a different way to do this, but I could not think of a better way to do this. Because basically what we need to do, like let me zoom in here. We need to basically represent each of these spaces here. In fact, I'm going to do this over my demo station instead. Here. Each of these spaces essentially represents a rectangle. So let's look at this one right here. Trying to do this backwards kind of weird, to be frank. So this rectangle right here, we want to encapsulate this whole thing. The challenge here, so the challenge here is trying to figure out, how do we detect this when this is open? So my thought was, what if we just, you know, because we don't necessarily care if it is an open space. We just care to know that something is there. So if we have a fake boundary at the end of the parking space, that encloses the whole rectangle as if it's an individual rectangle. So that's what we're going to do is we are going to enclose every single one of these parking spaces as if it's its own rectangle, and then be able to detect each of those rectangles individually. And that sounds complex, but it's actually, and this is what I'm talking about. Once you start to see these tools in action, then you start to, the wheels start turning in your head, and then you start to understand, oh, wow, I can do some really cool things that I did not realize I could do with OpenCV. All right. So let's come back here. So we're going to leave this alone for now. We do need to pick up here with the parking lines because we are going to use this parking lines here. So the first thing that I want to do is I basically want to wrap this whole parking lot in a big old rectangle. And the way that I can do that pretty easily, and this is where we start to deviate into the territory of this is not going to work for other like generic parking lots, is we can use a special function called bounding rect. And what bounding rect does is it basically detects a binary. So this is like a black and white thing. And what binary rectangle does is when you pass in this whole image, it's going to detect, okay, where is the outlying values of the parking line. So it's going to detect this top left corner over here, and it's going to detect the bottom right corner over here, and basically like give us the coordinates of this to be able to draw a big old rectangle around this. Okay, so let me demonstrate how this works. So so I'm gonna say we're gonna get the x, y, w, and h equals cv2 dot bounding rect parking lines. Okay. Bounding rect. Sorry. Okay, so you might be wondering, what do each of these values represent? So the x represents x and y represent the x and value and the y value of the top left coordinate here. So that would be somewhere right around the top left over here. And so then you might be wondering, what does w and h represent? W and h represents the width. So w would represent the width of the whole rectangle. So that would represent the width of the parking lot. And then h would represent the height of the parking lot. And so obviously using these 4 coordinate points, we can actually draw a whole rectangle around this whole thing. So you might recall from our last live stream how we drew rectangles is we had to give it 2 points. We gave it the top left corner and the bottom right corner. And so the way that we can do that, so we basically already have the top left corner. That is the x and y. And so the bottom right corner is just whatever the x plus w, and then the y plus h. So let's go ahead and draw a rectangle around our parking lines here. So I'm going to do that this way. So cv2.rectangle, parking lines. So we need to pass in 2 points. So point 1, like I said, is going to be the x and y. So that is going to represent the top left of the rectangle. Point 2 equals x plus w. So that is the top left corner plus the width of the rectangle. And then the top left corner again represented by the y value plus the height of the rectangle. So it's going to go from around 200 here to about 800, whatever that is there. So plus h, and then I'm going to give it a color of white. So because remember we're actually not using this one. We're using the grayscale version here. So color equals 255, 255. 255, and I'm going to make this a really thick line. So the way that we do that is thickness equals 50. Now let's go ahead and show this. PLT show parking lines. CMAP equals gray. Okay, so now we have fully enclosed the parking lines here. Okay, so the next thing that we need to do is, because we're jumping ahead a little bit, we are going to be using a special function that actually can actually detect what are called contours. And so what that is actually going to detect is everything that it determines to be kind of like a shape within the image. So if we ran it right now, it would detect all the rectangles, but it would also detect this outer rectangle because there is a contrast here between the white and the black line. So basically, the only thing that we want here is these rectangles in the middle. We actually want this border here to essentially blend in with the rest of the background here. And so the way that we can do that is actually pretty easy. So what I'm going to do actually is I'm going to invert the colors of this image, and then I'm going to take the inverted image, so we just have the white rectangles, and then just apply them right onto a brand new black background. So that might sound a little bit confusing, but it'll make sense here in a second. So the way that we do that, so let's first invert the image. So I'm going to say inverted parking lines. And so this function that I'm about to use only works, I believe, with a grayscale image, since we're using binary values here. So what that is cv2 dot bitwise not is parking lines, and let's parking lines. Okay, and let's go ahead and view that. plt dot mshow inv parking lines. CMap equals gray, not Gary, gray. Okay, so you can see we just inverted the colors there. Now, like I said, we just want to grab this center part here and apply it to a pure background. Now, when we want to get just part of an image, that is actually referred to in the image world, I guess, as a region of interest, or ROI. I know that is confusing to you finance people, who ROI means return on investment. So the way that we grab the ROI here is basically, again, we are working with arrays of numbers here as NumPy values, so we can actually just use some indexing to actually grab the ROI. And because we already have the rectangle that we defined here from here, we can actually use these coordinate values to grab this rectangle appropriately. So the way that we do that here is I'm going to say ROI, again, ROI meaning ROI equals region of interest. ROI equals inverted parking lines. So we want and this is where things can kind of get a little bit confusing, because we're used to, when we work on a Cartesian plane, we usually do x comma y. In this case, we actually needed to do the y value first, so we went from y to y plus h. I don't know why my wife's vacuuming right now. She knows I'm live streaming. X to x plus w. Yeah, like so. Okay, and so that is grabbing a region of interest. And just to show you that really did that, so plt.mshow. Oh my gosh. Could not think there for a second. CMap equals gray. Okay, so that just grabbed the center here. Now we want to apply this just to a pure black background, and we can actually create our own pure black background with a special function from NumPy. And the way that, so if you recall correctly, a black background is essentially just a bunch of zeros. And so NumPy actually has a function called zeros. And so I'm actually going to call even though this is a background, I'm going to go ahead and call this parking spaces, since we're going to keep applying on top of it. So we're going to use this function of NumPy called mp.zeros. And basically what we need to do is pass in how many zeros we want in the array. And we already know how many zeros we want. We want it to be the exact same dimensions as our original parking spaces. So all we can do is do parking lines dot shape. So this is this. It would be basically the same. I guess I could have done this too. Inverted parking lines dot shape. Doesn't really matter. It's going to be the same. dtype equals np.uint 8. So this is nothing but a bunch of zeros, and I'll just go ahead and show that really quick. So again, nothing fancy here, and I could even display this. So plt.mshow parking spaces CMap equals gray. And now that is just a pure black background, and there is nothing here but just blackness. Okay. And now that we have this black background, we can go ahead and take that region of interest and apply it on top of this space here. So the way that we do that is basically the same way that we grab the region of interest, except in reverse order. So the way that we do that, so parking spaces, and we actually probably could have done this as one function. Well, yeah, we could have done this as one function. So parking spaces y plus h comma x plus w. So that is again just saying, okay, we wanted at these coordinate values equals ROI. All right, now plt.imshow parking spaces cmap equals gray. Okay, so that is all the rectangles representing our parking spaces. So now you can see where we're starting kind of heading the direction. So I mentioned that we wanted to get to this point where we have just these rectangles representing the parking spaces, and that we'd eventually call this special function that would just detect the parking spaces. Now, these rectangles are still narrowly close together. So what I want to do is I actually kind of want to widen the spaces in between the rectangles. And what we could do here, and again, we're using our creative hat here. This is not, there's not necessarily one right way of doing things here. We are going to use a special function of, and I think we actually did this in our last week's live stream too. We're going to use a special function of CV2 called erode. And what erode does is it basically kind of, shaves down the lines of these rectangles here. So it's going to make these rectangles a little bit smaller without necessarily shifting them around. They're still going to be in the same position. So the first thing that we need to do is we need to create a kernel, and that this kernel is just going to be an array value of ones, and this kernel is just basically going to move over the image and then just slowly erode just a little bit of the rectangle, so that way when we run our contours function, then it can more seamlessly detect where these rectangles are at. So let's first instantiate the kernel. So kernel equals numpy.ones. We're going to just make it as 7x7 array, 7x7, dtype equals np.uint8. So there's not really a right or wrong answer as far as like what is the right kernel size. You could go smaller, you could go larger, if you want to see what this kernel looks like though. So it is just, like I said, just a bunch of ones, and it's just going to be passing over the image and slowly eroding it away. So the way that we do this here is eroded spaces equals cv2 dot take a guess, probably won't surprise you, erode. So we're going to pass in the parking spaces, then we're going to pass kernel equals kernel, and then you can have a number of iterations of how many times you want that kernel to pass over your image. Obviously, the more iterations you pass over, the more it's going to erode away your image. So we're just going to set it to equal to iterations equals 2. And then we're going to view this. So plt.imshow eroded spaces cmap equals gray. What happened there? Oh, I passed in the wrong one. Whoops. Not parking lines. I meant to say parking spaces. There we go. So now you can see, so let's look at this one really quick. So you see we have the original rectangles here, and now we look at these. It's the same rectangles, it's just that the borders of the rectangles are eroded away a little bit so that the black lines in between the rectangles are a little bit thicker. So, and the reason, again, that we're doing this is then when we go on to our next step, we have a better probability that this find contours function is going to be able to find each of these rectangles appropriately. And folks, we are now on the home stretch, kind of. Not kind of. I mean, we are on the home stretch. I just don't know how long it's going to take to talk through this. So yeah, this is everything that we've been doing so far has been leading to this point of where we actually want to apply this function. This function would not work. I could have tried applying this find contours function on this first raw image up here, and it would not have done much. In fact, whenever I first started to work on this project at the Starbucks a couple days ago, I tried doing the find contours to try to find the parking lines, and it did a horrible job of doing that. So I had to get creative, and so I recalled, let's extract out the parking lines and make them black and white, and then wrap a rectangle around them. And I had to get really creative to get to this point. So now that we got to this point, then this find contours function works much better. So the way that we do that here is we are going to use this function called find contours, and find contours passes back 2 different return values. To be transparent, like the second return value we're not going to use, and I don't remember what it does. Jose Portilla does explain it in this course, but I don't really remember. Again, we're not going to use it, but because it does return, I do have to set it. So empty spaces. So we're going to get back our empty parking spaces, And then so this second one is called hierarchy. I can't remember what hierarchy necessarily does, so I apologize for that, but I do have to account for it because it is being returned. So we're going to do cv2.find contours. All right, and then we're going to do eroded spaces. cv2.return. All right, and so then I can't remember what these are. So then we have to pass in like a mode and a method for what we do. And I can't remember. So this is looking for external contours. So I think what the hierarchy is there's a difference between external and internal contours. And I want to say, like, let's say I had some like black dots in here. If I ran this function and I was looking for both kinds of contours, the black dots would represent the internal contours, whereas the rectangle would represent the external contours. We are just looking for external contours here, so we're going to do return external, and then this next one. So I think here the method. This is just whenever it actually returns the contours, it just defines like how many, like how specific do you want to get with how many points are returned. We are just going to keep it simple, so that means the way that we chain these together. So chain approx simple. I know I'm doing a terrible job at explaining this specific piece, but just trust me, this code does work. So just ran that. Now we are ready. So let me just show this here. So what this represents is all of the contours that are inside of the image here. So there are actually a number of them inside in here, and now we can actually draw these back on top of the image. And it looks like there's a lot in here, but if I actually run a length here, length of empty spaces, you will see 16, which actually represents the number of rectangles that we do have on here. So let's go ahead and draw these back onto our image. So the way that we do that here is, let me move my face out of the way again, sorry. For space in empty spaces, we're going to draw the contours. So cb2.draw contours. All right, so we're going to pass in our eroded spaces, and then we need to pass in our contours. So contours equals space, so that is the thing that we're iterating through. Now we need to get the contour index. So again, the contour index here is representing that hierarchy thing, and so don't worry about that too much here. I believe -1 does represent external contours, so we are going to stick with that. And then I'm going to set it to be green. So color equals, remember, RGB. So R will be 0, G will be turned up all the way, blue will be turned off. So that is 0, 0, 255, 0. And let's make this a thickness equals 10. Okay. Did I do that? Did I need to convert that? Hold on. I don't know if I needed to convert that to a color image first. Oh yeah, I needed to color. I don't think that that probably did not work because I didn't convert the color here. Okay. That's fine. So eroded spaces. Here, let me run this cell up here again because I need to get the eroded spaces. Where's the eroded spaces cell? Okay, so I need to run this again. So I forgot this was in a grayscale format. When we draw a color on top of it, it needed to be an RGB. So I need to convert this once again. So eroded spaces. Spaces equals cv2.cvt color, eroded spaces, cv2 color, gray to RGB. Okay, now that should work. Now let's view this. All right, so plt.imshow, eroded spaces. All right, so now you can see here, just as we were hoping for, we can now successfully detect each of the empty spaces here because we have represented them each here with the green color. So these, recall, we still have the empty spaces still saved into this variable, which means that we can apply them to whatever image that we wanted. So we just applied them back to our image that we've been working against, but recall that we actually can just apply them back to here now. So now we're really bringing this thing home, and there is one more thing I do want to show, and that is simulating, well, what does it look like if a car is parked into a parking spot? And so that is actually a new function that I also learned thanks to Stack Overflow, that will basically, we can simulate, because just giving you a preview down the road, when we actually apply our computer vision detector that actually detects when a car is in a certain location, we're going to grab what is called the centroid of, because it's going to draw a bounding box here. Let me show with my demo station again. Here, let me grab a car. Okay, so let's say a car's parked in the parking spot here. When the computer vision detector starts, it's going to draw a rectangle around this car, and then the center of the rectangle is actually referred to as the centroid, and then we can represent that centroid with X and Y values. So I'm actually going to simulate what that's actually going to look like here in the code. That way I can show, I'm going to draw green rectangles for the empty parking spots, and then I'm going to fill in a blue rectangle for where a simulated car would be parked. And put it all together with this final little bit here. Okay, so let me go back to sharing my screen. Whew. I knew that there was going to be a lot to cover in this. That's why I kind of did. I usually spend a little bit more time with an introduction, but we're getting close to the end. But I knew there was a lot of material. But I hope this was an exciting, or has been an exciting stream so far, because I personally found this to be more interesting, one of the more interesting streams that I've done. Okay, so first thing I want to do, remember, because these are destructive images, anytime we do something on top of an image like this, this eroded spaces variable is now like destroyed. There's no way to get like the green out of here unless I perform some special stuff. Like there's not an undo button per se. So with that, I'm actually going to do a copy of our parking lot, and so CPL copy equals colorized parking lines.copy. So CPL just stands for colorized parking lines. So I'm going to make a copy of that. Now I want to simulate where a parked car would be. So I'm going to call parked car equals 800 by 400. And so if you look here on my X and Y graph, so 800 by 400 would be this square here, right here. So that is the fourth square in the top row. So now we can start to basically do that. We're going to simulate how to actually detect if that simulated car is in the parking spot. So here's how we do that. So for space in empty spaces. All right. The first thing that we need to do is check if the car is in the parking space. The way that we do that is with a special function. I'm going to call this car in space. So this is actually going to be the value that I'm saving this back to. So car in space equals cv2.pointPolygon. Hold on here. Sorry. Something went goofy here. I'm just making sure my stream is okay. Okay. Point polygon test. So we need to pass in the contour here. So the contour here represents our polygon. And then we need to pass in our point. So our point is our parked car, and then measured. I can't remember what the measure dist variable here is, but we're just going to set it to equal false. Basically, what this is doing is saying, okay, it's going to return a value that says 1, a value of 1. I don't know why it's not a Boolean value. I've never checked this. If it is 1, then the car is in the spot. If it is not 1, then the car is not in the spot. So that's what this is going to say here. So this is so then we can use a little bit of if and handiwork here to actually draw the contours appropriately if the car is in the spot or not. So if the car is in space, so car is in space, not space equals 1. So this is in the car. Here, let me make a comment here. Car in the space. All right, so then we need to draw our contours. So cv2.draw contours, cp, and then we're going to pass in our copied image. So contours equals space. Okay. Contour idx equals -1. Okay, and remember, I want this to be a blue filled in square. So blue is the last color channel, so R is going to be 0, G is going to be 0, and then we're going to turn blue all the way up. And then recall, if you want something to be filled in, I just said filled in because I was typing thickness. So thickness, if you want it to be filled in, you just put -1. So that is if the car is in the space. Now let's say if the car is not in the space, so car is not in the space. Then we're going to do the same function, except draw the rectangle a little bit different. Car, or I'm just going to do it else. cv2.draw contours, cpl copy, contours equals space, contour index equals -1, and then we're going to go back to our green color, just outlining it in green. So 0, 255, 0, and then thickness equals 10. Okay, so what after running this, obviously you can't see anything because we're going to show you here in a second. So what just happened is it filled in the rectangle, the simulated rectangle here, fourth one, top row, and then everything else is going to have this green rectangle on top of our colorized image. And to prove it to you, let us view the final product, and we will wrap things up here. Drum roll, please, people. plt.mshow, cpl, copy, and there we go. That is it. I personally think this is one of the coolest projects I've ever worked on. I think it's just really fun to see like how something can all come together, because now I think you can kind of see where we're going with this project. Is, you know, I would actually say this is the harder part of the project, because you'll see the next stream that we'll do, we will actually start to apply the actual detector. And what the detector here is basically doing, the only thing it's doing is it's just grabbing the coordinate value that we simulated here, and then we just apply this into this code here. The heavy lifting, in my opinion, of this project is just trying to figure out how do we actually detect these lines appropriately. But so now you can kind of see the light at the end of the tunnel, if you will. You can see how we are going to start putting all these pieces together to actually use our webcam over here to create this whole legitimate project. So we're getting close to the end here. If anybody has any, does anybody have any last minute questions? Feel free to drop them in the chat. So, because I'm going to start wrapping up here. Just for your awareness, there will not be a live stream next week. I'm actually heading to Disney World on Sunday with my family. And we will be there all week. We fly back on Friday, so I will not have time to prepare the next live stream. So I'm hoping to do one again in 2 weeks. Yeah, actually in my opinion, this is the most complex part of the project. From here on out, I mean, I think the next one we're actually going to show how to do the actual detection of the car, which is actually way easier than this piece here. And then we might do one final live stream where we actually put everything together. So where we put this same code here together, where we fire up this webcam, it detects the parking lines, and then we use one of my like toy cars over here to actually detect it in the spot. So hope you all enjoyed this live stream. I did a lot of talking. Whew, I am winded. I hope you all enjoyed this one. I am officially in vacation mode. So thank you all again for watching. I really appreciate it, and I will see you all in 2 weeks. Thank you.